Hello everyone and welcome to this talk. Today I'll be discussing my engineering research project, which is about detecting asset cascading failures. It is a fairly common problem that when an asset is repaired, it is often followed by a future repair on the same asset or another asset within a short period of time. This is what I'll be referring to as a cascading failure. So if these circles here represent assets, then it might be observed that the green dot fails, then a couple of days later, the orange dot fails, followed by a future failure in the gray dot not long after. Obviously, this is not a desirable circumstance. If it can be detected where these cascading failures are occurring, preventative measures can be implemented to fix the problem before it occurs, potentially saving a lot of money. This project is using complex network analysis to detect where these cascading failures are occurring. Data was provided by a mining company for repairs on different pumps within their 3 sites. Using this data, a complex network is constructed, similar to the ones shown here, to perform analysis on. First, let's talk about the data I was supplied with. In total, we have 88,545 work orders spread across 5,655 assets. Around 58% of these work orders are for corrective maintenance, which was the only work order type that I'm looking at today. The work orders come from a 5-year time period between 2015 and 2019. The histogram on the right shows the frequency of the number of work orders per asset on a log scale. From this graph, it is noted that most assets have quite a low number of work orders and only a few have a high number. From this data, a network of nodes and edges is constructed. The nodes represent the assets and are connected together with an edge if a work order is created for both assets within a specified time window of each other. These edges are assigned a weight based on the number of occurrences of this. So a higher weighted edge means that the assets connected have a co-occurrence of work many times in the data. Additionally, only corrective maintenance is considered for now, as we wish to consider cascading failures of assets, and this is most common amongst corrective maintenance work orders. This diagram shows my steps that my program uses to construct the network. First, the data is imported to Python and non-corrective work orders are removed. The NetworkX Python package is used to construct the network. The assets are added as the nodes, and then edges are placed between these nodes when work occurs within a set time window in the data for the assets. NetworkX calculates the network measures that I will show soon. And finally, we export this network to a program called Gephi to show the network visually. The results of this will be shown on the following slides. The first one of the network measures that I'll be discussing today is community detection. A community in a network is a subset of nodes that are densely connected to each other and weakly connected to other nodes within the network. In terms of assets and work orders, for our network, a community is a group of assets that frequently have corrective work occurring within a small time window of each other. This network here shows just a subset of the whole data we have. This is only using 3 months of work orders from the start of 2019, as the full network is far too large for one slide. This network is using a 24-hour connection window. So if corrective work orders are created for 2 assets within 24 hours of each other, a connection will be present in this network. The network has been colored to show the communities present amongst the assets for this period of time. Ranking nodes as important to a network is done in many ways. One way of doing this is looking at the node's degree. The degree of a node is the number of edges that a node has. In this case, using weighted edges, it is the sum of all the weights of the edges a node has. This highlights the assets in which corrective work in that asset is surrounded with corrective work on many other assets within a set time window. Using this method, however, will give a bias to assets that have lots of work orders in the data, as they would have more connections just by chance. To alleviate this, the degrees can be normalized. We simply divide the degree of each node by the number of work orders made for that asset. This removes the bias and highlights the assets that may have the most volatile failures. An interesting thing that can be seen in this is that the nodes with a high normalized degree are grouped together in the communities that we saw on the previous slide. This indicates that these communities typically have a large number of corrective work orders made for the assets within the community when a corrective work order is made for one asset in that community. These communities have the highest frequency of co-occurrence of work. This network is similar to the one seen in the previous two slides, in that the connection window has been set to 24 hours. This network, however, is using all the work order data instead of just the 3 months. And I have removed all the edges with a weight less than 14, and then all the nodes with no edges remaining have also been removed. The number 14 is chosen arbitrarily. In this case, it gives a graph that isn't too big but isn't too small. A couple of things can be recognized from this network. Firstly, there are self-loops present, indicating that these assets commonly have corrective work done soon after corrective work has been completed, potentially indicating a poor quality of work. Secondly, we can see a couple of chains of assets. We have called the nodes at the start of these chains superspreaders, as a corrective work order in one of those assets leads to work orders in other assets, which lead to more work and so on. This is cascading corrective work. The networks that we have seen previously have been using a 24-hour connection window to connect the assets together. 24 hours is a very small time window. The time window in this graph here is set to 7 days. So if a corrective work order occurs on two assets within 7 days of each other, an edge is added to the network. This makes the graph much more dense in that it has many more edges. The figure shown is for the full data with edges of a weight less than 25 removed. If you compare this to the graph seen previously, where edges with a weight of 14 or less are removed, you can see that there are many more connections in this network. The full network has over 4 million edges if none are removed. The same network measures explained previously can be applied to this network. In this graph shown here, community detection has been run and the communities of the network have been colored. I've made a table here of the most important assets according to the network structure. Degree ranking discussed earlier is the number of edges a node has. So these are the top 5 assets with the most connections in the corresponding networks. Eigenvector centrality I haven't discussed, but essentially it ranks nodes as important based on how many important nodes it is connected to. This is the same concept behind the Google PageRank algorithm. You can see in this table that there are many assets that appear multiple times for different measures and between different graphs. These are the assets that I recommend looking at first when attempting to correct this cascading and co-occurrence of work. So it has been found that complex network analysis can be used to identify where co-occurrence of work is frequent and potentially highlight cascading failures amongst assets. These insights changed based on the connection criteria defined. There are a couple of limitations that come from this method. The first is that only work orders that correspond to failures would be considered. Right now, we only have ones that are labeled as corrective work. Looking through the descriptions of these work orders, it is clear that they do not all correspond to failures. Some of the work orders are labeled as corrective when they are just inspections. The other limitation is that by looking at the strongest connections of the network Assets with a low number of work orders throughout the 5 years of data will be excluded. For example, if only edges with a weight greater than 25 are considered, then all assets that have less than 25 work orders in the data will be automatically removed because they will never have an edge with a weight greater than 25. I have listed a few ideas here for what future work can be done on this topic. Firstly, a deep comparison to real-world connections would be valuable. This would include analyzing how the pumps in the data are connected physically and electrically and comparing these connections to the ones identified in my approach. If a lot of the stronger connections present have a real-world connection, then it likely means my method is correctly detecting cascading failures. The second is that currently only work order creation dates have been used when making connections. It would be useful to connect assets when the completion date of one work order is within a time window of the creation date of another. The next one is to introduce preventative work orders into the network, specifically looking at when preventative work on one asset is followed closely with corrective work on the same asset. This may indicate that poor work quality has occurred. Finally, this one isn't in my slides, but when we presented these findings to the mining company that provided us the data, they identified that some of the strong connections I identified were already known and preventative measures had already been implemented. These still showed up in this analysis because the whole 5-year data was being analyzed at the same time. I would suggest doing a temporal analysis of the data to see how the network changes over time. This will identify where preventative work has improved the situation or not, and give us insights as to how the dependencies change over time. Thanks for listening.